Chapter 24, Problem 46, Holiday Resnick. A charge of minus 9.0 nanocoulombs is uniformly distributed around a thin plastic ring lying in the YZ plane, with the ring centered at the origin. A minus 6.0 picocoulomb particle is located on the x-axis at x equals 3.0 meters for a ring of radius of 1.5 meters. How much work must an external force do on the particle to move it to the... So here's a picture of what's happening. We have the YZ plane. The ring is in that plane. And then right up above the center is a charge. And from this to the ring, this distance is x. So this distance here would be the square root of x squared plus y squared. And the distance from here to the center is r. We start by knowing that V is equal to work over Q, which equals to potential energy over Q. And also work is equal to the change in potential energy. So when we look at this, potential energy is equal to V times Q. We're going to follow this path and then this path to the center. So we can have potential energy is going to equal V times Q for one path, then minus V times Q for the second path. Voltage is equal to K times Q divided by R. We're just setting it up now, so hopefully you'll see exactly what's happening in a second. So potential energy is the change in voltage. So we'll say potential energy is equal to, we just put it up this way, K Q. Now that Q is coming from the ring. This is the Q we're talking about with the ring. Over R1, we can say, times Q. This is the Q that we're moving. KQ over R, KQ over R, times the Q that we're moving. KQ over R times the Q that we're moving. Minus K Q Q over R2. Now this is going to go to 8.9 times 10 to the ninth, that's the times the ring, which is times (9.0) times 10 to the minus 9 times the charge that we had up here, which is 6 times 10 to the minus 12 coulombs. So the 6 times 10 to the minus 12. So we're going to subtract these denominators. One is 1 over 1.5 meters, that's the radius, minus x is 3 squared plus the distance y, which is r in this case, 1.5 squared. We'll pause and do the calculations. So that is equal to 1.8 times 10 to the minus 19 joules, which is also equal work. Let me quickly explain what summarize what we did. We had a particle of a minus 6 times 10 to the minus 12 coulomb sitting above this ring of charge, which was 9 times 10 to the minus 12 coulombs. And we had this distance, radius of 1.5 meters. So we realized that work is just a change in potential energy. So we got the potential, the change in these two potential energy. So voltage, K, Q over R, that's what that is, times Q. And this Q was the charge that we were moving. And we just set it up, the change in potential energy, Q1, Q2, Q1, Q2. 1 was the charge we're moving. 1 is the charge of the ring. And we got the differences between these two potential, the potential that went to the ring from this point to this point, and we took from this point to this point, we just took the differences, and we did that by using the differences in the R's.